Yep. All good.
And it'll get the, okay.
I'm just gonna point it there.
I don't know.
All good.
Okay. I guess I can just do that. So, yeah, here's the talk, electroplating and anodizing. Okay, so I want to give a disclaimer. I am in no way an expert on this. This is just a hobby that I picked up in the spring. I thought it'd be cool to learn about it and explore it. I knew nothing about it before. I don't know a whole lot about it now, but I can tell you what I've learned over the last few months and kind of my journey so far. And I think that these talks are good for that. You know, if anybody gets a new hobby that they want to just kind of share their experience with somebody, with the rest of the group, this is a good opportunity for it. If so, we're now accepting talks in October and beyond. So just let me know. Anyway, the other disclaimer I want to give is that I was not all that successful at electroplating, especially. I think there's still some tweaking to be done to perfect it, and it's not as easy as it seems on the YouTube videos. But anyway, I'll get into the details about all that. So I just don't want you to. I want to temper your expectations a little bit. But anyway, there's a lot of cool stuff on the way. So there's all kinds of. Well, let me just first tell what these electroplating and anodizing means. Electroplating is adding a thin layer of one metal on top of another. And that is almost, well, it's for a lot of reasons. Actually, I'll talk about that in more detail. Galvanize, there's a lot of different terms that you hear in this field, and galvanizing is one that you hear a lot too, and actually that is just a very specific form of electroplating. It's when you coat iron with zinc, and it just prevents the iron from rusting. So you hear like galvanized chain
steel.
Yeah. Chain link fences are usually galvanized so that they don't just purely rust. And so it's just a particular form of electroplating. So that's, if you hear that term, that's what that means. Anodizing is a different chemical. All these top two involve chemicals and electrical currents running through them. Anodizing changes the color of the metal, and also its electrical and corrosive properties. We'll talk more about that all later. But you can also just change the color. So both these things will change the color of the metal and the appearance of it. You can also accomplish that with painting. And I kind of viewed painting as is this better than painting? You know, like it's like the standard, it's super easy to paint something, and all this work that I'm doing here, it's just kind of always compared to the gold standard of, is it better, am I getting a better result than if I just painted it? And then these are other terms that you hear a lot, and they just are different ways of treating the metal. Annealing, you heat it and slowly cool it, and that makes it kind of bendy and more malleable. Tempering, you heat it to a low temperature and cool it rapidly. And hardening, where it's actually kind of brittle because it's so hard, heat it to a real high temperature and cool it rapidly. Anyway, these three we're not going to talk about at all. It's really these top three that we're going to talk about. So I always like to stand back and put everything in perspective, and I love the periodic table of the elements. It's so cool. So you can see the metals that we're mostly going to be talking about today. We're going to talk about a lot of different metals, but I've sort of circled the ones that we're going to talk about the most. And these, the aluminum is kind of a beast in its own category. That's the guy that we're going to be anodizing. But all the other ones are the ones that are commonly used for electroplating, although also like palladium, platinum, rhodium, these other guys can sometimes get involved. But you can see it's really, a lot of times it's these three right here, copper, silver, and gold. I didn't do any silver and gold because that's expensive, and we'll talk about that later. But I did a lot of copper. So cool thing about the periodic table, I don't know how much chemistry you all know, but things in columns tend to behave the same way. So like this column, well, first of all, this column right here are the noble elements, and they're the most stable ones, and every other element kind of wants to be like them. So this column likes to gain an extra electron, because then it'll be more like these guys. It'll fill their orbitals and they're a little bit more stable. And this column likes to lose an electron, and this column likes to lose 2 electrons. And so anyway, it's a cool way of laying it out so that you can see, kind of predict, like this one will kind of act similar to that one. And in the metal category, it's a little bit more loosey-goosey, but you still can see some of that. All right, anyway. I'm going to talk about anodizing first because this is the first one that I sort of played with. And so, okay, what is anodizing? It is when you take a metal and you coat it with a metal oxide layer of that same metal. So you oxidize the outer layer of the metal. Why would you want to do that? It makes it corrosion resistant. It's like it's pre-rusted. You know, and it's less likely to interact with acids, and it's harder a lot of times. It also changes the surface resistance. If you anodize aluminum, it goes from, aluminum's normally very conductive, it'll conduct electricity, but once it's anodized, the surface does not. The inside of it still will conduct electricity, but the surface does not. And that actually comes up. But the main reason we do it is because you can change the color. And there's actually two different things that are happening with anodized metals, and they're completely different on how they change the color. And we'll talk about that. So first I'm going to talk about titanium. So like a lot of piercings and jewelry is titanium, and they can change the color of it by anodizing it. Magnesium, all these other strange elements that you never hear of are also in the same boat. I'll show you this little video of titanium being anodized. Hopefully the sound will work. Okay, I need to make it a little louder. All right, we'll try that. Okay, so he's got basically two titanium rods here, and he's actually using just heat to anodize it. You can also anodize it by running an electrical current through it in an acid, which is what we'll do with the aluminum. But he's cheating, he's using heat. But he's got interesting talk about it.
You want to keep the torch moving, as heating one area too fast will make the colors appear too quickly, and often you end up overshooting the color you were aiming for. The colors always appear in the same order, and we'll talk about why in a second. It starts with a light yellow, then gets more bronze, then pinkish, then purple, then vibrant blue. Once you hit blue, it'll start to lighten past that point, and eventually it'll hit a silvery white. If you keep going, you can get another round of colors, but they're usually muted comparatively. You just aim the torch.
Okay, that's the little clip there. So what's happening with this? And so the color is determined by the thickness of the metal oxide layer. And the same thing happens. Some of us made bismuth crystals out back earlier in the summer, and the color of those crystals was determined by how quickly it cooled off. And so if it cooled off slowly, it created a thicker metal oxide layer. And so here in my next slide, or over here actually, it'll show how the thickness of that layer determines the color. So it's actually not air down here, it's metal. Okay, so we got metal, film, and air. So light, when you have that really, this is all microscopic. This is, you know, like the wavelength of light, so like nanometers, okay? And when you have just nanometers of oxidized metal, the light can just go right through it like it's water, okay? It's not stopping. But some of the light bounces off the surface, and some of it goes through it and bounces off the bottom surface, right? And so if it's a certain thickness, the wavelengths will add up, or they'll actually cancel each other out. And if it's a little bit thicker, then they actually end up in sync, and they have constructive interference. And if you make it thicker yet, then it's destructive again. And that's why he said, you know, if you keep going with it, you'll actually get another round of colors because you'll keep repeating this process. So anyway, the cool part here is that it's just this tiny little film. It's actually the same reason that if you look at soap bubbles, they have these scintillating little colors on it. It's because the same process is happening of constructive and destructive interference of the light bouncing off of like the top of the bubble and the bottom of the surface of the bubble. And that creates all those different colors. So that is what happens when you anodize titanium. You create this titanium oxide layer. Aluminum, though, is completely different, what happens. So we'll talk about that now. So when you anodize aluminum, here's like an electron microscope, or I don't know, some sort of detailed picture of what happens to the surface of aluminum. You end up with these, the aluminum oxide forms these porous little tubes, and then you can soak this in dye, any sort of dye, and well, certain dyes, and it'll fill up these little holes, and then you can seal it off, and then that surface of the aluminum is permanently that color, whatever color you want. And that's why I've got little bottles of blue, black, green, and because you can dye the aluminum whatever color you want. And here's just a picture of it. So here is the actual unoxidized aluminum. Here are these porous aluminum oxide layer, and then it's sealed off up here with some hydroxide stuff. So anyway, so you can just dye aluminum whatever color you want. I don't know if any of you have seen this. This is if you add mercury to aluminum. It's a time-lapse picture of, and I have no idea if this is kind of what's happening, but if it has the same sort of feel to it, where aluminum is creating these like pillars of weirdness. So anyway, that's aluminum and mercury. Okay, now we're going to start doing this stuff. So again, we're anodizing. So we're going to be creating on the anode. So the anode will be the aluminum, and we'll be running the electrical current through it. I'll talk more about what this bath consists of in future slides, but we just have an acid bath here. And when you run this electrical current through here, this is telling you what's going on. I always like to know, one of these anodes usually is making bubbles, or one of these terminals is usually making bubbles. And I always like to know what the bubbles are. Like, are they going to kill me? Are they going to explode? What exactly is going on here? I watched one YouTube video where the guy said that he was afraid the bubbles might be toxic, so he bought some detoxifier and added it to the solution, and he thought that would protect him. And I'm like, what are you? They're hydrogen bubbles, okay? Like, they're going to explode if they're going to do anything. And they're probably not going to even do that. But they're not going to kill you. And you don't, what if this detoxifying thing's not going to do anything? So anyway, you got to know what the bubbles are. It's my personal philosophy. And also, the bubbles are useful to knowing if it's going right. You know, like if the bubbles are coming off the terminal that you're not expecting them to come off of, then you probably got something wrong. So anyway, when this is aluminum and you run the electrical current connected like so, this is the positive and that's the negative. The aluminum on here, this is kind of how I remember it. The aluminum loses 2 electrons. They get sucked up here into the positive terminal of the battery, and so it becomes aluminum, a positive ion of aluminum, okay? And it just sits there and it says, well, I don't like this. I'm going to take a bunch of electrons from the oxygen that's in the water, and then I'll be neutral again. And so it just becomes aluminum oxide, all right? Meanwhile, at the other terminal, so the water has gotten the oxygen stolen from it, so the hydrogen moves over here, it gets some extra electrons from this terminal, and it becomes hydrogen bubbles. So when you're anodizing, the thing you're anodizing shouldn't make any bubbles, but the other terminal should make hydrogen bubbles. So this up here, I really like a lot, this mnemonic, because I constantly connected them wrong. And so anyway, positive is anode. It's not as easy to remember as you might think. So anyway, so this is what I did. So for anodizing aluminum, a lot of people recommend, I think there's a lot of ways to do it, but most people recommended battery acid or sulfuric acid. And so it was actually hard to tell from the internet, the vast repository of information that it is, how concentrated the sulfuric acid should be. Because a lot of places said 30% battery acid, and a lot of places said 30% sulfuric acid. But battery acid is 30% sulfuric acid, so like, what are they talking about? Anyway, I just went with 20%. You can buy sulfuric acid at Lowe's or at Walmart. They're both drain cleaner. Turns out this stuff is red, and that can't be good for trying to, like, I'm sure it'll make your thing red. So like, I ended up using this one.
Probably red so you can see it in the drain, maybe.
Yeah, I'm sure they must have added something to it because it's normally transparent. Anyway, then the cathode, the other terminal, because the anode is the thing that you're treating. The cathode can be all these different metals. It just has to conduct electricity, right? There's some disadvantages, like the aluminum. You can't really use aluminum because it's going to eventually get a coating. It's going to become anodized, and then it won't conduct electricity anymore. A lot of people said good things about lead, so that's what I used. I don't know if the next picture shows it, but that is this tank right here. I should put its normal cap on. I was going to demonstrate, but I think that actually would be hard to do while I'm giving the talk. Unless we have a lot of extra time. And there might be better things to demonstrate than this. But basically, you can see here, I made a sheet of lead, and I just bent it around there with a little nubbin sticking out here, and then that's 30% or 20% sulfuric acid in there. And then I've got this special cap that I made so that when I screw it on there, this part is over that nub. And so then I can connect one of the terminals to the battery to that. I connect the other terminal, it's actually not a battery, a power supply, to the aluminum thing that I'm anodizing. And then I just dangle it in there. And away we go. So the amount of electricity to use, man, there's a lot of different things. I just wrote a smattering of different advice from the internet here, but I think it doesn't really matter. This power supply goes up to 25 volts, and I think you just want to get some good bubbles forming that it shows that things are happening, and just run it for a while. I don't think it really matters that much. I just kind of winged it, and it worked. So there's all kinds of advice, like number of amps per square inch and stuff. Yeah. Anyway, I wrote it here if you want to go by that. And that's it. Oh, one other thing is you'll note if it's working, the voltage, so this here power supply is actually super simple to use. There's 4 knobs. The bottom 2 knobs adjust the amperage, the current. And so if one of them does like big changes and the other one does small changes, you just dial in on those bottom 2 knobs how many milliamps you want, and it'll just keep it at that current. So it'll change the voltage as needed to maintain that current. And so if you have it in that setting, the constant current setting, you'll notice that as you're anodizing, the voltage will slowly increase because of the surface of the aluminum will become less conductive as it becomes anodized. Oops. And some places recommended bubbles, but or like agitation. Like some people put a aquarium bubbler in there to keep it all mixed up. I think that's more important with the electroplating than this because the bubbles aren't forming on the aluminum, they're forming on the other terminal. So then you soak it in there for a while with electrical current going through it, and then you take it out, spray it with like distilled water or reverse osmosis water. And then this tank here is just baking soda and water. And you just plop it in there to neutralize the acid. It goes, psh, it's very satisfying. And then you take it out of there, spray it again. And then it goes into one of these heated tanks with the dye in it. So each dye is got its own temperature that you're supposed to use. But anyway, it's usually about 10 minutes at about 140 degrees. And then after that, you dip it into the nickel acetate, and that sort of seals the top so that the color is stuck inside of that surface of aluminum. All right, so that is the theory. This is what I did. So I actually spent a lot of time and effort trying to figure out what the best tank would be. I wanted some wide mouth, something that was small enough to be portable. And initially I got glass, and I'm like, somebody's gonna drop this and it'll be all over the place. And so then I'm like, all right, we're gonna go with plastic. So I knew that adding acid to water is kind of a touchy thing, right? So it's absolutely critical to not add water to acid, right? Because the acid rips apart the water, and it just becomes an explosive reaction if you do it like that. So you always have to add the acid to the water, but it heats up, and I knew it was going to heat up, but I did not know how much it was going to heat up. And the first time I did it, I completely melted this into a little nubbin. And so then I learned to add it very, very slowly. And second time through, it did not melt it. but it got hot. So anyway, just be on the watch for that if you make your own acid solution. And then that's the setup I've got here. So my first run through, first you anodize it in here, then you rinse it, you neutralize the acid, you rinse it again, then you dye it in here, and then you seal it in here. And that's what I ended up with, is which you actually used for your art.
That was okay.
Yeah, and then I coiled them into little links, and you made art out of them. So it was the perfect circle of art. All right, so now we're going to talk about electroplating, and that's what these two tanks are. This one's copper and this one's nickel. And basically it's the same procedure. And actually I didn't stress this much on the first one, but it's important. Every time you do anodizing or electroplating, it's got to be no oil on the thing that you're treating. It's got to be very well polished, washed, degreased. Some places online mention etching it, like soaking it in lye, but then they say that it makes for like a hazy, less like a dull surface. I'm not sure why you would want that, so I never did that because I'm going for shiny, right? Okay, then the next trick is you got to create the electroplating solution. So in the first, with the anodizing, it was just sulfuric acid. But these are like a metal dissolved in an acid. The next slides will talk about how I made that. And then, you got to remember that the cathode and the anode are switched compared to the other one. In this case,
Understanding the challenge. Creating electroplating solutions.
Be quiet!
So you're
What was that? I don't know, I didn't like it. All right. So the cathode, the thing that you're treating, this is not right. This is wrong, I'm pretty sure. Because it's the cathode that is where you want the metal to be plated on instead of the anode. So I think I got that reversed. But anyway, it's important, it's the opposite electricity as what you were doing before. And same thing with the amount of electricity that you use. I think that this is more important with electroplating because this is probably something that would need a whole lot of playing around with to get it right. I think that, well, I'll show you my experience with it so far, but maybe if you kind of slow it down, you might get a more subtly plated surface. I'm not sure. But I think that is worth playing with. Oh, and then, yeah, the voltage really doesn't change as you electroplate, unlike with anodizing. I think agitation might have a better role here, or somehow stirring the solution. I did not do that. It just seemed like too much, but that might be worth trying. And then again, you rinse it off, neutralize it. You don't put it in the dye this time, but otherwise it's the same procedure. So with this blue one here, the copper sulfate solution, the way I made the solution is I just bought copper sulfate and added water. But so this is the anode, and it's just copper plates. Okay, and so what's going to happen is the copper will move from this plate into solution, and then from solution into your sample, or onto your sample that you're plating, right? But you kind of have to start with a saturated solution already, otherwise you'll just spend all your time moving it into the solution with the current. Does that make sense? I'm seeing some nods. So this was my first setup here with copper wires and copper plates, and then I added the copper sulfate solution, and then I'll show you eventually what I plated with that. Let's see next. This is me making the nickel. This is nickel acetate. And so this one I made the solution myself. So I got acetic acid just from Amazon, which is vinegar basically, 75% vinegar. But It's not vinegar. It'll burn your nose if you sniff it, and it's nasty stuff. So and it'll burn you if you touch it too. So anyway, I took these. It was kind of hard to get nickel, but I finally got these nickel plates, and I connected them with aluminum wire. And I knew that the surface of the aluminum would eventually not be conductive anymore, because as it gets anodized, while it's hanging out in all this acid and electricity. So I wanted to make sure I had a good connection here between the nickel plates and the aluminum wire. So I wanted to solder them, and I tried to use just a regular soldering iron, and that was like spitting in the ocean. So Hardik told me to get the blowtorch, and you got to heat up the whole plate. And I did. It was dramatic. The whole thing glowed. But anyway, I got some solder in there, and I made some good connections. And then so I've got these 3 plates over here, and these 3 plates over here, and they're all connected together. So these 2 plates are the anode, and this one is the cathode. And then I just ran that for a while, and this is what it looked like. It's bubbling away here, hydrogen bubbles. Those were the settings I had. And after, I don't know, I think it was about 3 hours of that, the solution became kind of this, I don't know if you can see it, kind of a greenish solution. And that's the nickel acetate. So that's how I made the solution. And I think that's how you would make like zinc acetate. If you wanted to electroplate with zinc, you would do the same thing. And I'm pretty sure tin you could do the same way. So. And then this is just kind of going back to this, except everything, it's a little bit different reaction. So here the metal, this is the, for example, the nickel plate. And here it gets some electrons ripped away from it, so it becomes 2+ nickel. And then, but instead of sticking around and stealing an oxygen from the water like the aluminum did, it just says, hey, I'm going to go hang out with this acetate in the solution here. And then the hydrogen ions, just to maintain electrical neutrality, end up going up this way and forming the hydrogen bubbles. That's a terrible description. But anyway, general idea is the hydrogen bubbles and nickel leaves here and goes in a solution. So here's a chart that I made with the help of ChatGPT. However, I have a disclaimer here in the corner that I caught GPT lying to me 3 different times in the process of making this chart, so I do not know how accurate it is. But some metals will plate on other metals better, and it's not always symmetric. Sometimes a metal will go onto, but it won't let the same metal come onto it. So anyway, it's just kind of an idea that like aluminum doesn't play at all with this. So that's these columns here. Chromium is, let's see, chromium here. It's not great. But anyway, most of the action happens in here with copper, gold, iron, nickel, silver, and tin somewhat. So anyway, it's good to know. So here are some of the things I learned. My first setup with the copper, I had copper wires. And it turns out those were the very first things to just be absorbed and plated onto the things I was plating. So I lost connection. So I had to replace my copper wires with aluminum wires. And then it worked. Yeah, so the copper goes away. And then the other thing was, this was me trying to nickel plate a penny, and it didn't really work that well. I mean, it got plated, but it's ugly, for one thing. I think I could polish that and make it shiny, but it also started eating away at the penny in here. I have the penny in there somewhere, and you guys can look at it. But so, I mean, if you're plating something that is like precious or important, you might want to monitor it carefully because it might destroy it.
I wonder if the reason is because pennies aren't 100% copper.
Yeah, they're like plated, and I think
they're like
that
98% copper.
I think they're zinc mostly with a plating of something.
Yeah.
Some sort of alloy?
Yeah. So maybe the zinc was getting free there. I don't know. I don't really know.
Copper is really soft. Nickel too. Copper and nickel are really soft metals.
Yeah.
So they have harder metals in there.
Yeah. So actually, we recently acquired a little melting furnace, and we've explored melting different metals. And at some point, I'm going to get like some good ventilation and masks and whatnot, and melt down some pennies and try to make a zinc acetate solution, because they are mostly zinc. But the problem we learn is that it can become a toxic gas. So. Yeah.
Might have said that.
Yeah. But so I don't know. That's just the same thing. So this is what I found. I tried. There's a lot of talk online of these things working, and then you try them and they didn't. And I think that a lot of people are interested in electroplating 3D prints. But the problem is, whatever you're electroplating has to have an electrically conductive surface. And so you can either coat it with something like this graphite, and that's what I use for these. But then it still caused pretty patchy results. And at one point, or actually a few different videos said that it conducts better if you rub it, or but it rubs off is the problem. And one person recommended putting it in like a tumbler with sand, and then that makes it more even and more conductive. But I just found that it rubbed off so easily that I don't know, I just wasn't seeing that result. But like this frog, for example, you can see the crevices here did not get plated. And as I was telling Hardik earlier, you can imagine the little copper ions as like little magnets that are just getting sucked up to him. And if there's something closer by, it makes sense they would just go here instead of working there all the way through the gauntlet and going up in here. So maybe that's something that will get better if you tweak the voltage and settings. Or maybe you just need to electroplate things that are pretty much basically smooth and without a lot of irregularities like that. So what else? Conductive filament is potentially a way to go, although everything I read online said that you get bad results. And I tried really hard to buy some electrically conductive filament to try it out, and it says on the roll that it's electrically conductive, but it has a 0 electrical conductance if you test it. So they're just lying, I guess. I don't know. I've yet to find any electrically conductive filament. What else? Yeah, so I said all that. And metallic spray paint, that's another option. I haven't tried that. That might be a good way to go,
I think
actually.
that's the one that I saw. These copper paint.
Yeah, and the video that you shared, I've got that next. That's probably a good way to go. But it's kind of hard to find that too, but I know that exists. So let's see. Okay. Here's that video that you shared, and I'm going to just show it. So somebody made this just unbelievably cool C3PO helmet by electroplating a 3D print. But at the end of it, he coats it, so he electroplates it with copper. And this is kind of the result that I got, this kind of pitted, gross looking thing, but he just polished the living snot out of it and it became mirror-like finish. So that's cool, all right, I didn't polish mine. But then it still is just copper, right? And copper will turn ugly very quickly. But the way he addressed that is he electroplated it with a pen, which I'll also show you in a minute, with palladium and gold, which you can see the prices of those. This is for 8 ounces. It's $100, and this is for 2 ounces. It's $120. So, okay, that wasn't a really expensive C3PO head that he made there, but let me just show you the video real quick. It's just a Instagram thing.
Jeez.
So yeah, he just prints it. We got that printer. We can do that.
We're good so far.
Yeah. He's got the same purple blue stuff I've got. This is the coating I did not use. So it's cool. It's not mirror finish though,
Right.
If you're going to compare that as a baseline, he ends up with a mirror finish. So a lot of sanding, which I did not do, or polishing. It's pretty good right there, but it's going to look bad quickly. And then this is the expensive part. So, ta-da! Yeah, that's pretty much it. Okay, so the thing that I actually found the most fun was the last thing I did, which was an electroplating pen, which I'll pass it around, but you can just electroplate extremely fine details. I just, for fun, plated George Washington's hair in copper. And you can also, there's these aluminum business cards, and you can like laser engrave a logo into them. And I thought, well, maybe I can just anodize parts of it and change the color. And that works, but it's kind of labor intensive, but it does work. So that's another thing that you can do with the pen, is you can actually anodize just parts of the card. But anyway, I thought we could demonstrate using the electroplating pen.
Okay, so you run a current through the quarter,
Yes.
which is made out of what are quarters?
Metal.
Yeah, nickel and zinc and
Okay,
probably something else.
and then you dip the. Is that the? Wait! Don't tell me. Don't panic. All right. So positive is anode.
Positive anode.
Okay. So the anode here would be.
The quarter. No, not the quarter.
Dang it.
It's the solution. Yeah. Sorry. It's so hard to keep that straight, though. Bye, Devin.
I'm just.
Let's
enamored
reload
by
it.
The process.
Yeah. So the little copper atoms. Oh no! Too vigorous. So the pen was only $15. These little tips were a lot.
That's where they get you.
Yeah. All right.
What are the tips made of?
They're just like basically dense fibers. Yeah. But
The anode is the solution?
yes, this is the anode. So the
This
copper
picture.
leaves it. Yeah, it's already in solution, right? And so it's floating around, and then it gets jammed onto there and
I
gives up
see.
some electrons,
I gotcha.
or gets the electrons back, so that it's neutral again.
Okay.
So I'm trying to understand why the solution is the anode and not the pen.
Well, the pen is.
Okay, so it is the
Yeah.
thing that's
Current's
actually
running through both.
Yeah.
Okay. All right. So it's the. Okay.
I think it's
the
probably ready.
solution sort of the way of the two.
Who's up next?
Yeah.
Yeah.
Nobody else is jumping to it.
I think I'd be going
Wait,
around
Mr.
getting
Washington.
anything metal in the house and just being like, what about this?
Yeah. I actually went around the house the last 3 months looking for things to electroplate or mess around with, and I couldn't find anything except quarters for some reason. I don't know.
Spoons, forks, knives.
I did. Oh yeah, that reminds me. I did a spoon. I lost it. It was a great demonstration thing, and I wrapped the titanium current wire around the neck, and then dangled it in the water. Anyway, that wire basically left a shadow. Like